Welcome back, fellow math explorers. Um, Today, our journey is actually centered around the Milman-Pettis Theorem, right, which is a pivotal bridge that artfully connects two fundamental aspects of mathematics. In general, in mathematics, we often explore spaces that possess a dual nature. So on one side, we have the captivating world of geometry, right, dealing with shapes and structures, and on the other hand, we have the intricate realm of topology, where continuity and convergence actually reign supreme. But what if I told you that, in the realm of uniformly convex spaces, these two facets actually harmonize in a way that is profoundly enlightening? Well, the Milman-Pettis theorem actually stands as a testament, right, to this harmony, as it actually reveals how the geometric beauty of uniformly convex spaces and the topological finesse of Banach spaces come together in a symphony of I would say, mathematical wonder. So let's not talk too much, right, and start our exploration with a definition. So definition. So definition. Thing. Let me just, for a matter of style, let me just drag it a bit down. Okay, so a Banach space um, is said a Banach space E, of course. So let me just write Banach space E. Is said to be, put it in color, uniformly convex. If the following implication hold: if for every epsilon positive, right, there exists delta positive, right, such that for every x and y in E, right, such that for every x and y in the closed unit ball, right, and norm of x minus y slightly greater than epsilon. This actually implies that, put it down, the norm of x plus y divided by 2 is actually strictly less than 1 minus delta. So this is, if this implication is actually satisfied, then we say that the space E is actually uniformly convex. So so the uniform, so let me just write this out. Let's take this as a, say, a remark. So the uniform convexity, is a geometric property of the norm, right? It's a geometric property of the unit ball. So this means that, well, it basically says that if you actually slide the whole of length, if you slide a whole of length epsilon, right, of length epsilon, right, in the unit ball, then its midpoint must stay within the ball, must stay within the ball of radius 1 minus delta, right, for some delta positive. So this would be the geometric interpretation of uniform convexity. So just probably as an example, so let me just write it in color. So consider for instance x and y being element of the unit sphere. X and y on the unit sphere. So this means, of course, that the norm of x is equal to the norm of y is equal to 1, right? So consider this in a uniformly convex Banach space. Right. So first thing is that, I mean, if x and y are close together, so if x and y are close together, so very close together means, I mean, the norm difference is actually, I mean, small enough, right? Norm of x minus y is small. Then the average x plus y, or the midpoint, x plus y over 2, right, is also close to the unit sphere. Okay, so now the second thing to observe is that uniform convexity actually imposes, so uniform convexity imposes a condition that if x and y, right, are not too close together, right, the midpoint x plus y over 2, right, must be significantly closer to the origin, to the center of the unit sphere than either x or y. So uniform convexity actually prevents the unit sphere from having sharp corners, right, or flat regions. So whenever 2 points on the unit sphere are actually relatively far apart, right, that means, I mean, the difference norm is actually large. I mean, the midpoint is actually forced to move closer to the center of the ball. So let's have a look at an example. So example, so assume that we are actually in the plane, so E equal to R2. So the Euclidean norm the Euclidean norm, so I mean the two norm, right, which is actually x1 and x2 are actually you don't need the absolute value, right, because it's actually squared. So the Euclidean norm is actually is uniformly convex. So this is uniformly convex, right? While the norm, the one norm, we just rewrite the definition, sum of the absolute value, right? And the infinity norm is the max norm. Just write definition, max of the value of x1. I mean, those are not uniformly convex. The set, I mean, the space E and O with those norms are, I mean, are not uniformly convex. Okay, so this can be easily seen by staring at the unit balls, right? So let's try to picture that somehow. So let's say something like this. Say we have something like this, and then you just replicate. Okay, so now let's draw. So this would be, for instance, the unit ball of E, right, for the Euclidean norm, right, for norm 2. And take another color. So like this here first. Put this. Okay, so now we have something like this. So this would be the unit ball. So this is the unit ball of E, right? For this is for the one norm. So I mean, this is actually uniformly convex, as I said earlier. This is uniformly convex, but the other one is not, right? Because if you take this point here, right, the midpoint is, I mean, it's obviously far away from the origin. So I mean, you can also do the same thing with by drawing also the unit ball of E, but for the infinity norm, which is nothing else than, which is the square, actually. Good. So this is also, this is unit ball of E, but for infinity norm. But again, this is not uniformly convex because of those points at the edges. Good. So now let's state the main theorem of this lecture. So theorem 3.31, right? So this is the Milman-Pettis Theorem. Milman-Pettis. So the theorem says that every uniformly convex Banach space is reflexive. So every uniformly convex Banach space is reflexive. So, okay, good. So, but before actually going to the proof, let's have a couple of remarks. Probably only one. So, remark. I mean, uniform convexity is actually, as I said earlier, right, a geometric property of the norm. So, let me write it again. So, uniform convexity is a geometric property of the norm, probably higher geometric property of the norm. Okay, so what does it mean? I mean, it means that so this means an equivalent norm need not be uniformly convex. Right? I mean, I think we saw that with the Euclidean norm, right, which is actually convex, but the one norm and the infinity norm are not uniformly convex. So, but on the other hand, right, we know that reflexivity is actually a topological property. Reflexivity is a topological property. This means that a reflexive space remains reflexive for an equivalent norm, right? So a reflexive space remains reflexive for an equivalent norm. So this is actually a striking feature of the Milman-Pettis theorem, right? That a geometric property actually implies a topological property. So this theorem will be very, very useful, right, in proving that LP spaces are actually reflexive, of course, for P actually strictly between 1 and plus infinity. So let's go back to the proof. So okay, so we want to assume that you have a uniformly convex Banach space, and then our goal is actually to show that the space is reflexive. So let xi be an element of the bijoule with norm 1, norm of xi equal 1. So put it in color. So we have, in order to show reflexivity, you have to show that xi is an element. I always fail to write xi properly. Xi is an element of the image of the closed unit ball in E via the canonical embedding G. I mean, remember, so let me write it here. So remember that E reflexive means that the bijoule is equal to G of E, right? And this means that the image of the closing ball, something the closing ball in B star star. So keep this in mind. So that is why you have to show that xi is an element of the image of the closing ball via G. Okay, good. So since J of BE, right, is actually is closed in A star star, right, the strong topology. And we saw all those, right? Just check out the video on actually reflexive spaces. So since J of BE is actually closed in E star star in the strong topology, it suffices, it's enough. It suffices to prove that. So let's call it R1 because we are going to refer to it later. Suffices to prove that for every epsilon positive, right? So there exists X in the closed unit ball in E such that the norm of xi minus g of x is actually strictly less than, it's less or equal than epsilon, right? Because we saw that the image of the closed unit ball is actually closing the strong topology. So this is the same as the closure of this, right? So being an element of so being an element of this is equivalent to say that you are an element of the closure, and being an element of the closure is actually materialized by this expression here. Okay, good. So now fix epsilon positive, right, and let delta greater than 0 be the modulus of uniform convexity. So modulus of uniform convexity is just defined as. So this is the so this is the inf of what of 1 minus the norm of x plus y over 2, right? Such that xy are element of the closed unit ball, norm of x minus y is greater than epsilon. Okay, good. So this is actually basically the delta involved in the definition of uniform convexity. So however, right, we know that the norm of xi is actually defined as being the supremum of the absolute value of the Joule pairing of xi and f, right, over the f in E star such that norm of f equals 1. Now by characterization of the supremum, by characterization of the here of the supremum, right? So there exists f the Joule space, right, such that norm of f equals 1, and the Joule pairing of xi and f, right, strictly greater than the norm of xi minus say delta over 2, right? But this is class norm 1, so this means right? This is something greater than 1 minus delta over 2. I will call this relation R2. Okay, good. Now put V, right? Put V being the set of neta in the bijoule, right? Such that absolute value of the joule pairing between neta minus xi, right, and F something less than delta over 2. Okay, so that V is a neighborhood of xi, right, in the topology sigma E star star E star. Okay, good. Now, since the image of the closed unit wall is dense in BE star star, right, with respect to the topology sigma E star star E star. So this is actually by lemma, I think it was lemma 3.4, right? Check the lecture out on reflexive spaces. So because this is dense in B star star, so we know that V intersected with J of BE is non-empty. Thus, there is this, right, X in the closed unit ball such that J of X is in V. Now our claim is that this X actually fulfills relation 1. So claim X satisfies R1. So for that, to prove this, we proceed by contradiction. So aiming to a contradiction, assume that the norm of xi minus gx is actually strictly greater than epsilon, right? We assume that x does not fulfill the relation 1, so this means exactly that the norm of xi minus gx is actually strictly greater than epsilon. So this means that xi is an element of the complement of gx plus epsilon times the closed unit ball in B star complement that I'm going to call W. Okay, so W is actually a neighborhood of xi, right, in the topology. Sigma E star star E star, right? This is because since BE star star is closed, so the complement is open, is closed in this topology. So W is actually a neighborhood of xi, right, in the topology sigma E star star star. So using lemma 3.4 again. Using lemma 3.4. So in fact, lemma 3.4 was just about state that lemma 3.4 actually state that the image of the closed unit ball in E is actually via the canonical embedding is dense in BE star star, right, with respect to the topology sigma E star star E star. So using lemma 3.4 again, we know that V intersected with W intersected with the image of the closed unit ball. I think I have to put it here, so that this is actually non-empty, right? Because this is actually finite intersection of neighborhood of xi, and it is still in neighborhood of xi, right? And remember that xi was an element of BE star star, right? And the image of G of BE and is actually dense in BE star star. So this is non-empty. So this means there exists now Y in the closed unit ball, okay, such that G of Y is actually into V intersected with W. Now writing that G of X and G of Y are element of V, right? We obtain, this is just by definition, right? So there is nothing. We obtain that the absolute value of f of x minus the dual pairing between xi and f, right, is strictly less than delta over 2. And also the absolute value of the same thing but with y, less than delta over 2. Good. So adding these two inequalities leads to we get, let's go step by step, right? We get this minus xi f in absolute value plus this with y minus this is something less than delta. So this means if you use say triangle inequality, then you get that f dual pairing f of x plus y, because f is linear, so minus 2 times xi f actually something less than epsilon and then delta, sorry. So this means I will only take one part of the inequality, so this means minus delta is actually something less than f x plus y minus 2 the dual pairing of xi and f. So this means you just bring this dual pairing between xi and f on the other side of the inequality, so you get, let me just write it, f of x plus y plus delta. But observe that f is actually a linear bounded operator, so this is less or equal than the norm of f times the norm of x plus y plus delta. But again, f is actually chosen to be, it's actually in the has norm 1, right? So this means that 2 times this dual pairing is actually strictly less than the norm of x plus y plus delta. So if you combine this restriction, so combining this with relation 2, right? Relation 2 was actually that joule pairing between xi and f is actually strictly greater than 1 minus delta over 2. So if you combine both, you obtain that 2 minus delta is actually strictly less than norm of x plus y plus delta. So this means, this is just basic computation, so you get that the norm of x plus y is actually strictly greater than 1 minus delta. So it follows by uniform convexity. So it follows by uniform convexity. So let me highlight that. That the norm of x minus y is actually less or equal than epsilon. Right? I mean, to see this, I mean, this is just the contraposition, right, of the definition of uniform convexity. So this is actually the norm of x minus 1 is less or equal than epsilon, right, which is actually a contradiction, so which is absurd. Since j of y is in W, right? So I mean, j of y being in W means that the norm of j of x minus j of y is actually strictly greater than an epsilon. But j is actually linear, right? So this means j of x minus y is strictly greater than epsilon. But again, the canonical embedding is actually an isometry. So this means the norm of x minus y is strictly greater than epsilon. So this is why you have the contradiction. So this is why you have a contradiction. So hence, x satisfies R1, right? And then we can conclude that E is reflexive. Okay, good. Okay, so let's conclude this lecture with a useful property of uniformly convex spaces. So proposition 3.32. I think so. So assume that E is assume that E is a uniformly convex Banach space. And let the xn might be, I should stop writing the full, be a sequence of element of E, right, such that let me just put it here, so that xn converges weakly to x, right? So this is weakly sigma E star, right? And the ellipse of the norm of xn is less or equal than the norm of x. both, then xn converges solely to x. Okay, so let me just highlight some important aspects. So you need A to be a uniformly convex Banach space. Like you need to have a sequence that converges weakly, and for which the limb sub is actually a cycle and norm of x. So in that case, you can conclude that the sequence xn actually converges strongly to x. Proof. Okay, so of course we may always assume that x is different from 0, right? Otherwise there's nothing to show. Otherwise the conclusion is obvious. Now consider put lambda n to be the max between the norm of xn and the norm of x, and the norm of x, and yn, define yn new sequence to be lambda n minus 1 times xn, and y equals norm of x minus 1 times x, so that well, lambda n actually converges strongly to norm of x, right, and yn converges weakly to y. Well, why is that? Lambda n actually converges strongly to norm of x because the limb sub of norm of x is also equal to norm of x, right? So this is okay. So why do we have weak convergence of the sequence yn? For the simple reason that you have an assumption that xn converges weakly to x, and you have strong convergence of lambda n minus 1. Okay, so under this setting, it follows that the norm of yn, or the norm of y, is less or equal than the lim inf of the norm of y plus yn over 2. Right, so only invite you to see proposition in 3.5, right? In the lecture on weak topology, right? Proposition actually basically state that if you have a sequence, say yn, that converges weakly to y, right, then the sequence is non-bounded, so the norm of yn, so the sequence is bounded, right, and the norm of y is also equal than the lim inf of norm of yn. So this is basically the statement of proposition 3.5 part 3. Okay, so here, well, to see why, here you have of course yn plus y over 2 converges weakly to y, right? So that is why norm of y is actually less or equal than the lim inf, right? So okay, so I think this is okay. Now, on the other hand, I mean, we know that the norm of y equals 1, right? Now let me just go step by step. This is the norm of x minus 1 times x, right? So this is 1, obviously. And again, this is just by definition norm for yn is less or equal than 1. So you have that, so that in fact the norm of yn plus y over 2 actually converges strongly to 1. In fact, you have if you have 1 which is actually less or equal, I mean, to see this, I mean, observe that 1 which is equal to the norm of y, right? I mean, you saw that this was actually less or equal than the lim inf of the norm of yn plus y over 2, right? Which is the lim inf is actually obviously less or equal than the limit of yn, or the lim sub, if you want to just like lim of this over 2, right? Then this is bounded by 1. So the norm of yn plus y over 2 actually converges strongly to 1. So you can see that the midpoint actually is far away from the origin, right? So we deduce from the uniform convexity. So we deduce from the uniform convexity that yn and y should be, I mean, here close together. We deduce that the norm of yn minus y actually goes to 0. Right, so this means by definition, so this is just lambda n minus 1 xn minus this was norm of x minus 1 times x, so this goes to 0, right? So now this means that the norm of lambda n minus 1, right, times the norm of xn minus x actually goes to 0, but this actually goes to norm of x minus 1, so you obviously have norm of xn minus x converging strongly to 0. So this just write xn converges strongly to x. So and then we are done. So this is basically what you wanted to prove. Okay, so good. So with this this is the end of the lecture, and thank you very much for watching, and see you in the next video.